Assalamu alaikum. I am Abdullah Abid, roll number 23I6110 from Fast Islamabad. And this is our digital logic design project, which is traffic control light. I am the lead of my team. I work with Muhammad Atikullah, and Muhammad Usman. We built a simple traffic light control circuit using two 555 timer ICs to demonstrate the digital timing principles. Now let's move to our view. Our project is a basic traffic control signal that stimulates the operation of traffic lights using 555 timer ICs. The system is designed to demonstrate how a digital circuit can be used to manage timed output, such as the sequence of traffic lights. It has practically application in real-life traffic management and help us to understand the core concept of timing in digital logic design. Now let's move to our circuit diagram. We simulated our circuit in LT-SPICE. This system is built up using two 555 timer ICs configured in a stable mode. One timer generates the primary clock pulse and the second controls the timing sequence of the lights. In this circuit, the timer are connected to control three LEDs representing red, yellow, and green traffic lights. The blinking sequence is handled through calculated timing using resistors and capacitors. The 100K and 47K resistor along with the 100 microfarad capacitors determine how long each light stay on. As you can see in the simulation, each light changes at a fixed interval, simulating an actual traffic light pattern. We tested the simulation multiple times and made adjustments to the register value to ensure the consistent and realistic timing sequence. This circuit is reliable and easy to understand, making it perfect for basic traffic signal demonstration.
At the heart of our circuit are two 555 timer integrated circuits, which are popular and reliable components for generating precise time delays and pulse signals. In our project, both timers are configured in a stable mode, meaning they continuously produce square wave signals without any external triggering. These continuous pulses are essential for controlling the LED light transition. To set up the timing cycles, we used specific combinations of resistors and capacitors. Specifically, we use 100 microfarad capacitor, 100 kilo ohm, 47 kilo ohm, 390 ohm, and 330 ohm resistors. These resistors and capacitors pairs define how long each LED stays on, controlling the duration of the red, green, and yellow light phases. The output from the timer circuit is connected to three LEDs: red, yellow, and green, which represent a standard traffic signal. Each LED light are based on the output timing signal from the circuits. We assembled all components on breadboard, which allowed us to easily modify the circuit during testing and debugging. Connecting wires were used to establish links between components, and their color coding helped in keeping the setup organized. Overall, the design was kept simple and modular so that each component function is clearly understandable. Every part contributes to the smooth transition between light phases, simulating real world traffic light behavior in a clear and educational manner. Now let's move on to the demonstration of our traffic light control system in action. As shown in the accompanying video, the circuit is powered by a standard 9-volt battery, providing enough voltage to run the timer and LEDs efficiently. Once powered on, the circuit immediately begins executing the programmed light sequence. The LEDs blink in the following order: red, then green, and finally yellow. Before repeating the cycle, this pattern closely mimics real life traffic lights used at intersections. The working mechanism involves the first 555 timer generating clock pulses, which are then fed into the second 555 timer. The second time responds to these pulses by changing its output state, turning on one LED at a time based on the timing configuration we have set. Each light stays on for a distinct duration. The red light stays on the longest to simulate a stop signal, followed by green and then a shorter yellow phase to indicate caution. These durations were carefully adjusted by experimenting with different resistor and capacitor values during circuit testing.
Here's a breakdown of how the system works. The first 555 timer operates as an oscillator, continuously sending pulse to the second timer. The second timer IC then interprets these pulses and switches the output between three states, which controls the LED. The timing interval are controlled by the RC resistor capacitor network connected to the 555 timer. The voltage across the capacitor causes the timer to trigger a reset, creating the on and off state for each LED. Especially, we are using timing logic to simulate a state machine where each light phase represents one state. Since it is built with basic components, the project not only demonstrates digital logic concepts, but it is also practical for educational purposes. It cannot be expand. It can also be expanded to control real road intersections using relays and sensors. To conclude, this project helped us understand the practical use of timing circuit using 555 timer. We learned how basic digital logic and hardware components work together to simulate a real-world system like traffic controls. It gave us a hand-on experience in calculating time delays, building stable circuits, and simulating output effectively. In the future, we can expand this project by using microcontrollers or adding sensors to make the system respond to traffic flow. Overall, this was a great learning experience for our team, and we enjoyed applying DLD concepts to our real world problems. Thank you.